everyone. This is Professor Jeff Wilkerson at Luther College with an introduction to Exercise 17, Kuiper Belt Objects from Astronomers as Observers and Experimenters, published by Kendall Hunt. So let's jump right in, and I'll talk to you about some of the learning goals that I have when I do this exercise with students. And maybe first and foremost among those is just an introduction to the number of objects that are out there. We look at 1 year and we say this many objects beyond the orbit of Neptune were discovered in this year, and look at all of them that are there. So we get a sense of how busy the outer solar system is with a lot of small objects. And so we look at that and we say this is really a good way to get a feel for that number of objects that's out there. It's not all the objects by any stretch, but it's how many were discovered in a single year. So it gives us a chance to take a look at those. Another thing that we do, another really interesting idea here that I like to emphasize when I'm working with this exercise is that we're doing population studies. Once we know the objects are out there, we can say, what can we learn about these objects? What can we do, given the vast number of them, to do a population study? It is not dissimilar in that regard from the work that we did in the distribution of clusters, star clusters on the sky exercise, where we looked at globular clusters and open star clusters, and we asked, what can we learn about the nature of the Milky Way from the distribution of those objects? Let's make graphs. Let's study where those objects are in the sky and start to think geometrically about where those objects are. We're doing a population study. We're looking at a whole bunch, a whole big population of these things. And instead of asking questions about the objects themselves, we were asking a question about where those objects lived in the galaxy. Here we're going to ask questions about the objects themselves, but there's a real resonance between these two exercises, and that resonance is built on this idea of doing population studies. And so I like to think of these two things together. We circle all the way back to what I've told you in other videos and maybe even written about in the introduction to the textbook, is that very challenging for me to do just a stars course or just a planets course. I like to do all of this because I like to look for those connections, look for those threads that connect those ideas across the different aspects of astronomy, what people might think of as very different realms of astronomy, very different regions. So what we do is we make a histogram, and we've made a histogram again. We're referring back to the cluster distribution, the distribution of clusters on the sky exercise. We've made histograms before, and a histogram is a very good way into understanding a data set, getting a first quick visual understanding of what's going on with a population type data set like this. Around these parts, I've probably talked to you before, I'm known a little bit for maybe doing too much histogramming. I histogram everything. I probably, again, told you before, I histogram trick-or-treaters as a function of the time they arrive at the door each year and try to understand the nature of what happens with trick-or-treating during the week or during year to year. I histogram everything, the normalization factors or the long-term photometric resolution for our research project that we talk about. We say, well, how good is our photometry? How good a job are we doing measuring the brightnesses of the stars? And we have a sort of full width standard deviation of a distribution that we look at, and I make histograms of those throughout the year, try to use that to understand what our nights can we use, what nights do we not want to use. In all of those things, what we do is we plot the number. You might normalize it a different way and plot a percentage or something like that up there, but we plot the number as a function of whatever variable we're looking at here. And here it's going to be size. We're going to call it diameter, even though these things may not be around. We're going to call it a diameter of the object, and we'll have some unit out there. And that might be tens of kilometers, or it might be hundreds of kilometers, it might be kilometers, it might be whatever it is however you want to break this down. It might not be kilometers at all. It might be fractions of Pluto's size. Might be an interesting way to histogram these. And if we say there are 4, let's say 1, 2, 3, 4 in the between 0 and 1, and 2 and 3 and 4 and 5, that might be 10. Let's make it 10, 20, 30, 40, whatever your unit is down here, depends on that. If there are 4, we draw a flat line across at 4 and then a straight vertical line down. And if there happens to be 2 in the next band, we do that. And if 3 in the next band, we do that. And then suppose we had 8, big jump up, and 7, and another 4, 5, and so on. And so we look at that and we'll say, okay, this is great. We might be able to learn something about this. Maybe we think there's a peak here. And if we think there's a peak there, we can say, okay, this tells us sort of the distribution of these sizes that we're looking at. One of the things you want to look for here, one of the things that we've not done in this exercise is we've not tried to subclassify these objects. We call them Kuiper belt objects, and people might take exception to that. Where we're looking at anything that's out beyond the orbit of Neptune, there are these small outer solar system objects. And there are certainly classical Kuiper belt objects. There are plutinos. There are different classifications of the way people might think about this. And you might start to do this. This is a thing that a population study is great for, is looking for subpopulations. So looking for, to say, what if there was a secondary peak out here? You could ask the question, why is there a secondary peak out there? That's probably a separate population of objects. That's probably different from this somehow. For some reason, we see these as different from this. And then we want to embark on a study of these objects. Remember what we're doing throughout this textbook. Remember what we're doing with this whole enterprise is to say we're making observations. We're thinking about how to analyze the data from those observations, and we're building a model of the physical universe, and then we want to test that model of the physical universe. And so now we build a model that says this is a different population of objects. Let's try to understand what they are, and then we can maybe build what data do we need to do that. We go get the data, and then we can build a new model that's more detailed, helping us to try to understand what the differences between these objects are, and so on and so on and so on, and we keep digging down through there. Now, let's stop here, pause here for a second, and say, we said these are bigger objects, but there's also a possibility that what we did when we started this was we said, let's assume all of these objects have the same albedo. They reflect the same amount of sunlight. If some of them have a higher albedo, they might reflect more sunlight, and they're going to look bigger to us. And these might just be objects that are icier, that have a shinier surface, and thus reflect more sunlight, and they appear bigger to us. They might actually be bigger. But then whatever they are, we want to learn more about them. And we want to say, let's go study their distribution. Are they less in the plane of the solar system? Are they more flattened in the plane of the solar system? Are they closer? Are they farther? What do we know? What can we learn about these things that's going to help us model them? Can we take spectra? Can we do all of these other things to start to dig in and turn this into a real project to understand these things? If we backtrack for a second, this idea that we assumed all of these things had an albedo of 0.1 would maybe make me even put a star right here on the diameter and say, this is a model-dependent diameter. This is, we're calling it the diameter, but it's actually dependent on a model that we built, and that model might be precise, but not accurate. It might be accurate, but not precise. It might be neither accurate nor precise, or it might be both precise and accurate. That is to say, we might be right. 0.1 might be the right average albedo for these things, but there might be a wide distribution of them. Or we might be wrong. 0.2 might be the right albedo for these things, but it might be a very narrow distribution of them, or it might be two objects, and those things that we just talked about apply to things that are here, but not to things that are here, and so on. Anyway, the first step into this kind of population study is to start to say, okay, there's something different going on here. Let's see if we can unravel it. Let's see if we can figure out what's going on. So really, one of the goals for this exercise, if one of the goals was just to understand that there's a vast number of objects out beyond Neptune, and we want to understand how that solar system is populated, another goal for this exercise is to reinforce how we do population studies, how we can just take first steps into doing a population study to understand what our next steps would want to be and how we might build a model and how we might think about taking more data in order to help us understand what's going on here, to look for subclassifications, to practice making histograms, whole lot of stuff going on there. Always remembering that we're building this sort of model dependent diameter right here, and that's, we're testing that model. But if it's a model dependent, that's fine, as long as we understand that we might be coming up with a test for that model and a way we want to tweak that model. There's another idea that's important here that probably plays into, it's probably worth thinking about as you do this exercise. These kinds of population studies are extraordinarily bias plagued. So we've talked about observational bias in other settings. I think we have an entire video out there, if I remember correctly, on observational bias. and there's an introduction to it at the beginning of the text. And so we want to think about where bias creeps into our observations. It causes us to think about things in a way that needs to be more nuanced, that we need to think about just a little bit more. And that is to say, certainly one way bias could creep in is we might be missing objects. If we're only looking in the plane of the solar system, our actual observational program might be missing objects that are up out of the plane of the solar system, and we need to cover more sky. Of course, it's hard to cover more sky, looking everywhere, and these objects are hard to see. So we might be biased that way. There might be bias in the certain directions we look. There's clouds of material that we don't know about in the outer solar system. Maybe not likely, but there's material out there that's obscuring some of our ability to detect this. But certainly smaller objects are harder to see than larger objects. That's always going to be a bias we have to deal with. And so these objects that are down here are hard to see. And you might see a distribution then that looks something like this, sort of straight edged on one side with a tail on the other side. And you have to ask yourself, why is there that straight edge? Why is there that flat edge on the left side? Very likely it's detection efficiency. Your ability to detect those objects is falling off rapidly right here, and you just don't see them. And the real distribution, you might be able to model that. If you wanted to turn it into a project and really think about that, you'd say, well, I might be able to model how inefficient I am at detecting these objects and correct these numbers that I have detected here for that inefficiency and say maybe the real distribution, the parent distribution looks like that. That's the observed distribution of objects, and that's the model distribution. That's the objects that actually exist out there in space that lead to this observation. That's the kind of work that people would do a lot of. So it's certainly the kind of work that I would do in my research work, is to say, yeah, we see this. You know, we see variable stars of amplitudes down to 0.05 magnitudes or 0.03 magnitudes. But our efficiency at detecting variable stars as the amplitude of variation gets lower and lower, gets much, much smaller. And so we have ways of trying to estimate, but it's just an estimate of what our detection efficiency is, and we try to correct for that. And so we look for that sort of thing. So this exercise is a great way to think about these kinds of biases that come in. Great way to think about just sort of practicing the art of making histograms and doing population studies and thinking about all the objects that are out there in the outer solar system. I hope you have fun with it. I like doing this exercise for all of the reasons that we've just talked about. As always, if you have any questions, don't hesitate contacting me. I'll see if we can work through that. So good luck with it, everyone. Have a good day.